So discussing and considering the parts per million scale and what that information from our monitor may give us and how we can interpret or use that information. So if we're looking at parts per million on a scale and convert that to a percentage, 1,000 parts per million is equal to 0.01%. 10,000 parts per million is equal to 1%. For reference, hydrogen sulfide, the IDLH is 100 parts per million. The two chemicals on our monitor that give us parts per million is carbon monoxide and hydrogen sulfide. Our oxygen is expressed as a percentage and the LEL is expressed as a percentage. However, knowing the parts per million and what that equals to in a percentage can help you identify if there is or how much of a substance may be displacing oxygen. One of the other sensors in our CGIs is oxygen, expressed as a percentage. Normal oxygen in the atmosphere is 1/5 of the total volume, about, but the specific percentage is 20.9%. If you recall back to our last video, 0.01% is 1,000 parts per million. So let's say this was 20.8%. That can be used to tell you that potentially there is 1,000 parts per million of some other chemical or substance or vapor in the air that is taking the place of that oxygen. That's how we can correlate the parts per million scale and the percentage to our actual oxygen percentage. For purposes of confined space monitoring, 19.5% and below is considered oxygen deficient and is a problem for breathing. 23.5% and above is considered oxygen enriched, and because there's more oxygen, would be considered a major fire hazard or would propagate burning or fire or explosion much more readily than if there was oxygen deficiency. The last information and reading from our CGI is our LEL, which is our flammable or explosive range. So that's in a percentage, it's on a scale. Because there's a lot of various flammable substances, they don't all burn within the same range, but our monitors are calibrated to a specific gas, and based off of that are correction factors. In order to protect ourselves and from a wide range of various flammable products, our CGIs will alarm generally at 10% towards whatever the flammable range is. And that protects us from a wide range of chemicals and flammable products, regardless of what their correction factor may be. So we don't need to know the correction factors, we just understand that there are various flammable products and a wide range of those. So in order to protect ourselves, the CGI will alarm at 10% towards what our calibrated gas is. In this example, you have 30% and 40% as the flammable or explosive range. On one side would be your fuel, the other side your oxygen. Right in the middle is where they mix and where they'll burn with the right amount of fuel, right amount of oxygen. In this case, if it's 30% is the lower limit, our alarm will alarm, or our CGI will alarm at 10% towards 30. So at 3%, our alarm will go off. So it's important to understand that just because it goes into alarm, that does not mean we are yet in a flammable environment. However, we should expect that the closer we get to the actual source, the more that will increase until we would be in a flammable range. Stated another way, we left station 1, we're on our way to station 2. Station 2 is our flammable range, whatever that may be. We've left station 1 and we're just a couple of blocks away. So we're 10% on our way to station 2. So we still have a little ways to travel, and we're not even in the neighborhood yet of Station 2. But now that we know this and we know our destination, we can start to take actions to start to mitigate whatever the problem may be or our flammable range before we get to Station 2. All right, so when we're talking about flammability ranges or whether something will burn or not, the lower explosive limit, upper explosive limit, lower flammable limit, upper flammable limit, flash point, fire point. For our purposes, really those are more or less the same, and we'll try to look at those, or should look at those in general terms. And it's all of that, the lower explosive limit, upper explosive limit is in the context of percentage of fuel and percentage of air. So in this case, we have some WD-40. We'll put some in our bowl. The can says flammable, we would expect it to be flammable. Turn the lights off. So we have our liquid. We will apply heat with the lighter in this case. It will increase the vapor coming off of the liquid and mixing with oxygen, which will increase it to the range that it's flammable. So we can see the flame start to burn the product, but as soon as we take the heat away, the fire goes away. It will begin to flash. We can see it flashing through some of the product, but very closely behind that is now on fire without any other heat applied. So the point, flash point, and the point where sustained burning will occur are so close together for our purposes in emergency response, doesn't really matter. If it's at the point it will flash, it's at the point it will burn. So in this case, still discussing flammability of liquids. We have a liquid in an open cup that clearly burns. When we change the vessel that same product is in and it's confined somewhat, just like a tank might be in confined space, if it finds an ignition source, we get a much different reaction. So another aspect of air monitoring, or whether or not a product in a tank will burn, is dust and a dust explosion, and something we should consider. Not something we can readily monitor for with an air monitor, but something based on the product that's in the tank we may be working in or that has been in there, and the kind of visual indicators of whether or not there's dust present. So in this case, it's coffee creamer. If this was in our tank, it's our dry powder product, doesn't burn. We may get a little bit of charring, but doesn't burn, nothing that causes a hazard for us. Now, if we change the makeup of that into a finer dust, even though it's still a solid particle, but now the fuel is more readily mixed with the oxygen, we'll get a different result. And again, this is only if you have heat or an ignition source that's applied. So even though we may be operating in these circumstances, we can still do that safely as long as we take some control measures. And that's what air monitoring gives us and drives, are some of those strategic decisions. So if we have our flame, we change the makeup of our cream. The cream readily burns. And we have the possibility for a dust explosion when you have larger quantities of solids in a tank with very minimal ventilation or movement of air. Then you have a collection of the dust mixing with the air, creating that hazardous and potentially explosive or flammable atmosphere. So in this case, we're talking specifically about our Q-ray CGIs. And our CGIs, the manufacturers may have changed for some of them, but what they read are the same. The CGI, the combustible gas indicator, has two toxic sensors, which is the carbon monoxide and hydrogen sulfide. And then it has the LEL and the O2. The LEL works in combination with the oxygen sensor because it needs a little bit of oxygen in order to read if an environment is flammable or not. So it's important that the oxygen is also correct. So if we use the method where we were not able to attach tubing and we had to lower the monitor, or if we wanted to come back later and see what our maximum levels were or our minimum levels, then with this CGI from this screen, if we hit the arrow button, so the button below the arrow, it will scroll through our different values. And these are cleared every time the monitor is turned off and then back on. And if you wanted to clear those values, you could do that hitting the button here under clear. But in this case, we don't want to clear it. We want to log the information for the entire incident. So our peak values have been 0 because it hasn't changed since we turned it on. Our minimum values have also been 0. You'll notice the STEL, which is the short-term exposure limit, and there's no numbers because the short-term exposure limit is based off of a 15-minute period. So in order to have a number, the monitor needs to be on for 15 minutes. At that point, the STEL or short-term exposure limit will start to appear in those two areas. Our time weighted average, in this case, is 0. And that's just monitor information, nothing specific that we need to know. If we continue to hit the arrow button through these last few screens, we do not want to enter communication mode. Simply hit the arrow over. And you're back to your main screen. And if you come back at a later point in time, same process, back to your peak, and it scrolls through all of the values we just discussed. So this is the MSA monitor. It's a passive monitor, meaning it takes a small sniff of the area you're in, versus the Q-ray monitor, which used a pump to draw air directly into the sensors. This one, in order to use tubing or to monitor remotely, requires an external pump, and that would be provided by Hazmat. Hazmat 50 and Engine 50 are part of any confined space or trench rescue response, specifically for that purpose of monitoring, as well as chemical interpretation for whatever environment we might be operating in. To operate this unit specifically and to go through the different values, once you've gone past your startup stage, you're at your monitor screen, clicking the down arrow takes you first to bump test. When you click it again, you'll notice a little mountain. That's your peak value since you've turned it on. Then your minimum, then your short-term exposure limit, time weighted average, and then through some just monitor documentation, the time, date, motion sensor, and back to your main screen. So part of monitoring and monitoring remote is the ability to monitor remotely in a space that we're not in, right, in a confined space. And in order to do that, we have a couple of different tools. On every engine, there is a box similar to this for monitoring and initial monitoring. Within the box is a radiological detector, not a part of confined space, something we don't need to worry about. There's some electronics and charging pieces, again, not something for us that we need to worry about. Really the two big pieces for monitoring are the tubing or the hose. Every tubing should be about the same length. It's about 20 feet. There's two different ends. One end has a fishing weight, and all that does is provides weight for the tube to get down to the bottom or to the level that you want to monitor. It's important to make sure that the tube is open and clear. The other end has a connection. There's two different monitors in the system right now, which we'll talk about. Specifically right now, though, this tubing is designed to work with the Ray monitors. When the MSA monitor, we get the equipment to monitor with that remotely for confined spaces. I'm sure it'll be similar and consistent as far as tubing, and the use doesn't change. So in this case, the end of the tubing simply screws onto the filter end of the CGI, and then the CGI will draw air from the bottom of the tube at whatever level you've set this to. It's important to remember that because you're not monitoring the direct atmosphere you're in, you have to give it some time to get through the tubing. General rule of thumb is about 2 seconds for each foot of tubing. So for 20 foot of tubing, 40 seconds or so is the time that what we're seeing on the monitor is what the environment was at the end of the tube 40 seconds ago, right? That shouldn't change within a minute. It's just important to know that if we turn this on right away and attach tubing, what we see here is not accurate of what is coming into the end of the tube, right? It's after about 40 seconds that we'll get that accurate reading. So when we're talking about remote monitoring, we have really two options to accomplish that. The preferred method and way would be to have our CGI remote from where that environment is, and we would do that with tubing, right? So we would attach the tubing to the end and put the tubing to whatever space we want to monitor. The other way to do that is more rudimentary and can be accomplished. Just takes a little bit more interpretation and is not as exact. So if we look at our tubing from the engine kit that we described, we may not use all of it, and even if we do, that's fine, to our level that we want to monitor. What we want to be careful of, we want a stable, a little bit probably above ground place for the monitor to sit, because we want to do continuous monitoring once we've started air monitoring until the rescue is complete and or our people are out of the space. Some things that could give you inaccurate readings and to watch for. If we use the tubing to tie off extra tubing anywhere, we can do that, but we need to be very aware and cognizant that we're not creating any sharp bends in the tubing that limits or changes the airflow, which would give us inaccurate readings. Or if we left the tubing on the ground and it were to be stepped on or get folded, again, you can see how that would limit flow. No different than LDH coming out of a hydrant. We want the tubing open to give us an accurate flow. The other way is with the monitor running, is to tie the monitor off to a utility rope and to lower the rope into whatever space you want to monitor. And then two things. You would know if it goes into alarm that obviously there was an environment. It would be alarming for something, but you may not know exactly what because you're away from where the monitor is and you can't read it. And even if it does not alarm, we can still use data from the monitor to tell what the environment was throughout the time we dropped it and then brought it back to the surface. As we're changing monitors and monitor brands, there's different capabilities or ways to get that information, and we'll show those individually. But essentially, you're looking for the peak value, and that would be all that you would really know, but you wouldn't know at what level within the space or what point that product or reading was. And you would have to kind of use whatever the situation gives you to interpret that, and is not as beneficial in a larger or deeper space because there's more volume and could be potentially be more layering, so you wouldn't know at what point in that space is accurate to what you're getting from the CGI in this method. You arrive on scene, we want to begin air monitoring as soon as possible. A basic rule using all monitors is to take your first sample from a small opening before opening up the space and to stand upwind of the location. Many times the mouth of the space is already open. Still remember that high concentrations of toxins and flammable gases can accumulate under covers and around openings, and depending on the circumstances, consider wearing an air pack. We want to start and continue monitoring early to create baselines and identify changes or trends of the environment within the space. Once we've done initial monitoring and created a baseline and established parameters, we can begin to monitor remotely in the space, generally with our tubing. Considering a vertical tank configuration, different chemicals, depending on their makeup and chemical properties, may become stratified within the tank or have different concentrations or levels within the tank. So it's important, especially for any vertical tank above 20 feet, that we break that tank into thirds and we monitor every 1/3 of that tank space. So we would have remote monitoring with tubing for the bottom 1/3, then tied off for the middle 1/3 and the top 1/3. And we would have those monitors running the entire time in conjunction with the personal monitor that the technician may wear with any entry team. At times it may also be necessary to monitor in a horizontal space that we may not have the reach for. In that case, we can use whatever available materials we have. In this case, wrapping the tubing around a pike pole to insert to the horizontal space of the vault to monitor that space either continuously or maybe prior to an entry team moving through the horizontal space into the next vault. The last aspect of confined space air monitoring is personal monitoring. Every entry team that enters should have a CGI with them, just one CGI for each entry team. Cut.